All right, good morning, everybody. My name is Luke Zio. I'm a statistician by training, and I've been teaching statistics the last 12 years. Uh, I have used Excel primarily to illustrate how to do statistical computation. And I'm going to start getting getting to know Excel pretty much more, and as a result, developed two courses about computing statistical function in Excel 2010 through 2013. So today I want to show you some of the things that you can do in Excel as far as analyzing data using the built-in statistical function. So as you can see on my screen, the two courses, the statistical function in Excel 2010, and I have the links. These are the Google shortcut links. All right, I'm going to go step by step to explain what I'm going to cover today, and then we will get started. All right, statistical function in Excel 2010. We will talk about how do we obtain the statistical function. We look at how to create histogram of data. And in particular, when we talk about constructing histogram, there are statistical rules that are suggested as far as what is the optimal number of bins used to histogram that will properly and the kind rule, the formula for determining the bin width of the class sample is given by W equal to times n quartile range. The n quartile range is the third quartile is the first quartile, and I will show that how to compute that in Excel. Divided by the cubic root of the size. All right, there is another rule that is used for determining the total number of bits for constructing a histogram in Excel, and that formula was given by a statistician named Stitches back in 1986. His formula says that the number of bins is given by one plus primary plus the log n of the subclass. All right, and after that, I will talk about rotation and regression. How do we analyze two quantitative data that appear to have some sort of linear relationship? I'll talk about rotation and regression. Then we will talk about random sampling in Excel. In particular, I will give a brief definition of what is a random sample. Why is it important to use random sampling in Excel? Or in real life, what's the data analysis? Why not set from as opposed to following the proper method to obtain the random sample? And how to obtain the random sample in Excel? All right, then we will wrap it up with a conclusion. And that's pretty much what I will be talking about today. And what next? I will be building a website dedicated to statistics and Excel, and get the people who are interested on the Excel side or the statistical side, get those people to meet and discuss, or via the Excel Advisor web page, generally on the same thing, this discussion about statistics in Excel. All right, I have courses on Udemy for the people who are interested in going there. My contact organizer at Gmail. And that's pretty much what we talk about today. Thank you. So with that, start showing mass extensions, and we will get started. So today my version of Excel is Excel 2013. You find out that from 2000, from Excel 2010 to 2013, all functions in 2008 at March in 2013. In 2008-13, they added a couple of, let's say about 5 or 10 statistical functions. Now, anyone with a version prior to 2007 may not see some of the newer functions because there have been Microsoft introduced a lot of functions starting with 2007. So anyone with a version prior to that may not be able to function that I'm talking about. All right, so I'm going to start with the descriptive aspect of statistics and how does Excel comes into play and how to use Excel for obtaining descriptive statistics. All right, so the data set I'm using is from the World Bank. Everybody know about the World Bank. Let me show the data. Here, 1 second. All right, so the data is from the World Bank, and the data is about the gross national income per capita for all these countries of the world. So here I have about, let's say, 167 countries. As you can see, it's all running. I'm going to per capita. Computed by and it's that's one side. I'll give you a explanation. So GNI per capita is computed using the World Bank Atlas method, and is computed as a gross national income divided by the number of people in each country, converted into US dollars. So that's pretty much the definition of GNI. So each country has gross national income. So you can see the data is measured on a numerical scale. In statistics, what we want to show first is, okay, what are the descriptive statistics of this data? And by that, I'm talking about the mean, the median, the standard deviation, variance, computing a metric called coefficient of skewness. So in other words, we will over so they can fully understand the nature of the data. All right. So there are, as you know, there are many functions that you can use. For example, the average is a function in Excel. So you can use average to obtain the mean of the data. Then you have other functions to compute median, standard deviation, skewness, range, minimum, maximum, curtices, and all these statistics I'm talking about. So instead of doing that, we will use a function in a library that is called a descriptive statistical library. The library first must be enabled. So when we click on File, so if you have any version that is 2010 and up, when you click on File, you will see Option. And after you click the option, you will go to the add-ins. And when you click on the add-ins, okay, here you will enable the analysis tool pack. If you are doing VBA, you can choose the analysis tool pack for VBA. So I use either one of them and then select OK. Once we select OK, so what Excel is doing, it's loading the analysis tool pack. The analysis tool pack is used by a data analysis like a statistician who want to be able to use the power of Excel. In other words, be able to compute more sophisticated statistics instead of using the one-by-one functions. So once we do that, all right, then we need to find out where the analysis tool pack is. So let me move my screen here. So when in Excel 2013, you will see the data tab here. When you click on this, you will see data analysis. So when you see the data analysis, it means that the analysis tool pack is loaded. So we can use it for our analysis. All right, so I'll double click on data analysis. When I double click on data analysis, I have a window given to me. So in that window, let me quickly talk about some of the statistical libraries that are there. One is ANOVA. ANOVA allows the analysis, statistical analysis of variance. So ANOVA single factor, ANOVA two factors with replication. So as you can see here, we can do analysis of variance using that library. Then we have a library called correlation. Correlation basically allows us to calculate the correlation between two quantitative variables. In other words, two variables that are measured on a numerical scale. And then here you have our descriptive statistics. So so here with descriptive statistics, you have other functions like histogram, Fourier analysis, moving averages, random numbers, sampling, t-test, z-test, etc. But since I want to talk about descriptive statistics, I'm just going to open up that window. When I open up that window, it's a matter of selecting the data. So let's say, let me just select the range of the data. So here included a label, in other words, the name of the countries on the first row. So I click on that to say that I included a label. Otherwise, Excel will display an NA because I have text as part of the selection. All right. So with that, then we have an output range. The output range is the place where we want to put the output. So two things. We can choose to put that output in a new window or just select a given area of the spreadsheet to put the data. So for demonstration purposes, I'm just going to suppose that I put the output range like here. So let's just put it in a new window just for people to see the output. I'm going to put in a new sheet. And here I will select all the statistics that Excel can compute. Summary statistic, confidence level for mean, KF largest, and KF smallest. When I do that and click OK, okay, so I guess the input range was clobbered. So let's go back and make sure here. Let's go somewhere here and double make sure that the output range was not changed. Control. All right. Let's go back one more time. Sometime when we select the data, all right, A1 through A68, new sheet, everything is selected. Reference. Oh. It did not. One more time here. All right. Just 1 second. I did select. Okay. So in my selection, I have non-numerical data. Just one. I want to make sure that I did not include text in it. All the data must be numerical. Let's go here. But first of all, let me show you what the output will look like after I selected it. So we will have a table that looks like this. So we have the mean. It will compute the mean of the GNI per capita, the standard error, which is just the standard deviation divided by the square root of the sample size, the median, which is a measure of the center of the data when the data is arranged in ascending or descending order. In other words, the median is a robust measure of the center of the data. Then we have the mode, which is the measurement that occurs the most number of times. So if a measurement is repeated several times, the most number of time in the data, that measurement will be the mode. Then it computes the standard deviation, the sample variance, the curtices. The curtices tell us how heavy is the tail of the distribution. So if the data is bell-shaped, the curtices tend to be small. Now, skewness tell us how skewed is the data. So for income, we will expect the data to be positively skewed because you would tend to have a few number of countries who make extremely high GNI per capita. So only a few group of countries that are extremely rich, and the majority of the countries will be on the left side. So we will expect the income distribution to be skewed. So as you can see here, the coefficient of skewness is 2.27, which is positively skewed. Then the range is just the difference between the maximum data point minus the minimum data point. So it gives us the minimum, maximum, and all this, and including a confidence level. So I'm going to go back here and just show it to you from the demo again. So I'm going to select the descriptive statistic. When I go back to data, here, data analysis, descriptive statistics. All right, I'm going to put in a new sheet. Input range. Yeah, it's complaining that my input range contain non-numerical alphabetical data, but I will look into it. But in any case, that's the table we will get when we select properly data, making sure that we don't have numbers or incorrect format in the numbers. So I obtained the descriptive statistics. Now, to properly show the data, in addition to the descriptive statistics, we need to construct what is called a histogram. A histogram is just a bar graph that is used to display quantitative data. And the purpose of the histogram is to show the shape of the data. For example, if the data is bell-shaped, with a histogram, we will know that the data is follow a normal distribution or the data is bell-shaped. If the data is skewed to the right or to the left, with a histogram, we will know that the data is skewed. So the histogram shows shape and all other elements that are pertinent or related to how the data is distributed. But before we can construct the histogram, first of all, Excel offers the histogram function. Let's show it. Let's open it up here. So if we select histogram, Excel gives us a window. So it asks for an input range and a bin range. The thing is, if we don't specify the bin range, Excel will default and create some bin range. And how do Excel determine the bin range? It has been suggested that Excel uses it tries to space them equally, and it has been said in the literature that they use the square root of the sample size to determine the number of bins. But Excel will scale the data automatically to find the bin range. But there are many instances where the scaling that Excel uses is not, I would say, optimal. In those cases, you are given the freedom to determine your own bin range. But how do we determine bin range? There are many. There are a few statistical suggestions to obtain the bin range. The first one is by Sturgis. Sturgis is a statistician who published that method back in 1926. And basically with the Sturgis method, he's saying use 1 plus 3.3, the log of the number of observations. So if we were to use Sturgis, so we will be doing, let's do 3.3 times the log base 10 of the number of observations. We have 167. Oh, I forgot to put the equal sign here. So we have 7.33, but the formula says use 1 plus that. So 1 plus 7.33, so roughly about 8. Roughly about 8. I think we have 166 countries, not 167. So here, one more time. 166. So yes, we end up with 1 plus 7.32, which is about 8. So Sturgis uses that. The Sturgis formula is not optimal. For example, here we have 166 countries, and Sturgis formula suggests to use 8 bins. So even if we had 200 countries, the Sturgis formula won't go more than 9 or 10. So in many practical cases, people tend to use Friedman and Dikanis. And the Friedman and Dikanis formula basically said to use 2 times the interquartile range divided by the cubic root of the sample size. But what is the interquartile range? The interquartile range is computed using the third quartile. So to obtain the third quartile, I use the function quartile.inc. So beginning with Excel 2010 all the way to 2013, Microsoft modifies slightly the function. So this function quartile.inc include the first and the last in computing observation and computing the quartile. So it's called quartile.inc. So I do that, and then I select the range of the data, which is B2 through B168. And the last argument or parameter is the type of quartile that I want. So if I want the third quartile, I will put 3. So when I put 3, I get 11,900. Now to obtain the first quartile, I can just copy that formula and change the 3 to 1. So here now you see the third quartile is the 75th percentile. So the 75th percentile of the income is 11,900. The first quartile is the 25th percentile. So the 25th percentile is 1,240. Now the interquartile range is just the difference between the third quartile minus the first quartile. So here you see the interquartile range is 10,660. So once we have the interquartile range, we can compute the Friedman and Diachronic bin width. So how does the bin width is calculated is 2 times the interquartile divided by the cubic root of the sample size being 167. So I put 167 to the power 1/3 to obtain the cubic root. So according to Friedman and Diachronic, we should use a bin width of 3,872. Some of you may want to Google it to read a little bit about choice of class interval because it's very important. Quite often people construct histogram in Excel using the default. In many cases it works, but there have been many examples, some example where the default doesn't work, in which case we have to use some sound statistical techniques to determine the bins. All right, so once I have the bins, then I have the bin width, then I have to calculate how many bins should I use if I was to use a Friedman and Diachronic method. And to obtain that, we will just take, here, 1 second. We will just take the range. The range is just the difference between the largest measurement and the smallest measurement. In other words, we take the maximum minus the minimum, we get the range. And Excel computed from the descriptive statistical function. So we get a range of $88,680. So we take the range and we divide it by Friedman and Diachronic bin width. So once we do that, we get a number of bins equal 23. So as you can see, if we use Friedman and Diachronic method, we are using 23 bins. Sturgis method, which was proposed back in 1926, resulted only to 8 bins. So with Sturgis method, the data will be compressed and we won't be able to see a nice distribution of the data. So I suggest that we use a method such as Friedman and Diachronic or Scott and Terrell. These are other methods. Sometimes you can use the default Excel, Friedman and Diachronic, just to see how the data look like, in addition to what the descriptive statistics is telling you. For example, my data, the descriptive statistics is telling me that my data is positively skewed to the right. So if I construct a histogram that doesn't show that, I will be suspicious. It will be because I didn't use an optimal number of bins. All right, then there are other methods, one suggested by Rice, etc. But I'm going to stop here, now that we know that we are using 23 bins. All right, how do I then choose my bins in Excel? How do I build the bins in Excel? To start building the bins in Excel, I start with the smallest GNI per capita. That's the smallest measurement, right? And here, once we have 1 second, we have the number of the bin width and the bin width and the number of bins. Then we need to find here, just 1 second here, bin width, all right, number of bins. All right, so we can come here and start with the smallest, and then we will be going by a bin width for 3,872. So we will add that to the first to get the second, and then from that, what I will do, I will just drag to populate until I cover the maximum of the data. So if I, like here, the maximum of the data is 88,870. So I need to stop here. So let's delete here. I need to stop here because if by going with the bin width, all right, I'm at 88,947, which is slightly above the maximum of the data, which is 88,870. So I know that I covered all the data, range. If I have not, then I just use the bin, start with the smallest, add the bin width, and you know, choose the tool to tell Excel that I want to increment by that, drag until I cover the highest data point in the data. Now that I have the bins pretty much defined, to construct the histogram, I will go to data analysis, select histogram, then input range, I will select my data. Let's come here and select the data, hoping it doesn't complain about the. Then here we need to select, instead of selecting the default bin, here I will come here and select the bin that I've calculated using Friedman and Diaconis. And here it will ask what type of chart we want. Instead of Pareto, I will just select the basic chart output. And then drop the you know, put the chart on a new window. So let's do that. So it brings the there's a long tail. So as you can see, there's a long tail to the right. So the data is skewed right. These are the few number of countries that are extremely rich, resulting to the skewness in the data. So if you look at this country, there are Western countries with high GNI per capita. And now here you have the majority of the countries, the poor countries, you see. So we will expect that income to tend to be positively or skewed or skewed right. And this is an agreement with what the descriptive statistic is that our income is positively skewed. All right, this is the histogram. If we didn't want to go through the trouble of finding the bins using Friedman and Diaconis method, we can just leave that field blank. So let's do that just for illustration. So again here, I come to data, select data analysis, select histogram. For illustration, I will pretend that I don't know any method for selecting the bin range. So I leave it blank. When I leave it blank, Excel will do the adjustment and determine the bin range for me. And as I say, okay, so this is the default using Excel. All right. Move chart. We will move it into a new window to see how it looks like. All right. So this is the default Excel program. Again, you see it's positively skewed, but we don't have as many, we don't have a long tail as in the Friedman of Diaconis chart. With the Friedman and Diaconis method, the tail is the times. So you have on the tail. We expect it to be longer. You have so many countries, 167, extremely rich, and then you have some in the middle, and then you have some who are very poor. So you would expect the tail to be more pronounced. So this, whereas the X1 doesn't, well, it showed that the data is positively skewed, and but it doesn't show long tail as the Friedman and Daikanis. So again, the suggestion is to, when constructing a histogram, not to rush and just choose the Excel default. There are certain type of data set where the Excel default do not work well. So with that, we can use Friedman and Daikanis, obtain our bin width, and start with the smallest, add the bin width to the smallest measurement, drag it to all the way till we get our number of bins. All right, I will close with that and talk about the next topic. The next topic will be about analyzing quantitative data. So here, let me open up the file. All right. All right, so we have two variables that are quantitative. A quantitative variable is a variable that is measured on a numerical scale. So the first variable is age, and the second variable is blood fat. And we want to see if there is a relationship between age and blood fat, and if it's so, what type of relationship it is, and how can we quantify that? You know, if the relation is linear, we can compute a correlation coefficient to measure the strength of the relationship between age and blood fat. If the relation is linear, we can build a simple equation or regression model between blood fat and age, so that, you know, we may be able to use the equation to predict. You know, so for example, if we know if someone is of a given age, what approximately the blood fat should be. So, of importance, when we have two quantitative variables, for the correlation, it doesn't matter. So, which one is called the explanatory and which one is called the dependent variable. But for the regression, it matters. So, quickly, let's go and select I'm going to select the data to first obtain correlation. So here in data analysis, I select correlation. So input range, I will just select the data. Here I select label in the first row. As far as output, I'm going to put the output somewhere here. Let's click OK. All right, it computed the correlation between age and blood fat. So as you can see here, the correlation between age and itself is 1, obviously, and blood fat and with self is 1. Now, correlation between blood fat and age is 0.837. Now, when we see some number like that, okay, first of all, the correlation is a number between -1 and 1. If it is closer to 1, the more it's closer to 1, we say that the two variables are positively correlated. And if it's closer to -1, we say the two variables are negatively correlated. If it's around 0, we say there's no association or correlation, or there's a very weak correlation between the two variables. But here, based on the fact that it's closer to 1, we will say that age and blood fat are positively correlated. What it means is that as age increases, as we increase in age, the blood fat tends to also increase. That's a positive association. But one thing about the correlation is not resistant to the presence of outliers. Outliers are data point that could be extreme data point that could show up in the data. For example, one with a wrong age. So if we type the data and we have an age of, let's say, 150, so it was a mistake, but it shows in the data as such, or we have the wrong blood fat content. We put 1,000. So it will affect the correlation. So one way to go about understanding the relationship between quantitative variable is to obtain a scatter plot of the data first. So we select the variable here quickly. I'm going to do a sample scatter plot. So the scatter plot shows that indeed there is a positive association. As we increase in age, so does the blood fat. So the blood fat increases as a function of age. As age increases, the blood fat increases. And when you're looking at the trend, this is a nice trend. There's no outliers. So if there were outliers, you could find a data point that is somewhere here or somewhere apart from the others at the top here. So the data doesn't show outliers, so the correlation coefficient is okay, you know. But if the correlation, if the data has outliers, then we need to do the correlation coefficient with and without the outliers and try to explain to whoever is in, you know, in charge of the data that we found a suspicious data point or an outlying data point that could have an impact on the correlation coefficient, so that we have with and without. We have to always show the two. All right, now that we computed the correlation coefficient, we found that it was 0.87. Now I want to construct a regression model. To construct the regression model, we need to know two things. One is called the explanatory or independent variable. That's the variable that explains. For example, if I have age and blood fat, age explains the content of blood fat, much like education level and income. So more education, more income, or fertilizers and fruit or agricultural yield. If we use fertilizers, we will tend to have more crop. If we don't use fertilizers properly, or we don't use them at all, you know, then the crop yield will not be enough. So the variable that explains is called an explanatory or independent variable. And the resulting variable is called in statistics the dependent variable or endogenous variable. So in regression, it's very important that we know which one is which. So like here, age explains blood fat. You know, older we get, the higher the blood fat content will tend to become. Just like education and income, education will tend to explain income. So education will be called the explanatory or independent variable. Now that we know them, first of all, let me put this plot in a new sheet. I'll put in move the chart into new sheet so that we can see the chart. So here I can select formatting, you know, chart design to format, just to show it. Here we will put we can put the title. I'm not going to worry about that since we are pressed with time. But once we have that, to build the regression model, we select the data point. So now you see all the data points are selected. Once the data points are selected, we right click. We right click and we select add trend line. So add trend line, let me go back and, so add trend line, let me go back here and we select my data. So right click, add trend line, yeah, should have a window to show which type of trend to use. So one here, trend line here on the left side. So we can select on the left side on my Office 2013, it shows on the add chart element trend line. We can select linear trend because we have a linear relationship. When we do that, it put a linear equation on the data. Okay, oh, here's the trend line window. It was hidden here. So we have the linear, we added the linear trend line, but we want to add also the equation. So I would say display equation. So I would select display equation. And I would say display R square. R square is a measure of fit. In other words, let's just add them first and then explain. So here we selected add linear because we have a linear relationship. Then we say display equation on the chart because we want to see the regression equation. Then we say display R square. All right, if we do that, we can then go back. Let me select, I'll make the font bigger so that we can see the equations in R square. All right, let me move it. All right, so here's the equation. Y equal 5.3207x plus 102. So in statistical terminology, the 5.32 is called the slope, and the 102.58 is called the y-intercept. So let's suppose that somebody is 40 years old. How would we predict that person's blood fat? All right, we will replace x by 40 and do the math. So 40 times 5 approximately will be 200. 200 plus 100.0258, it'd be 300.258. So if somebody is 40 years old, this model is saying that practically the blood fat will be about 302.58. Let's go to the data. Up here, where's the data? Here. Here's the data, all right. 40, roughly, let me find somebody who is 40. You see, somebody is 40, the blood fat is about 303. So the regression is doing well. We predicted 302.58. Now, R square measure is a measure of a fit. How well our model is doing if we just use age to predict body fat. It's saying that if we use age alone to predict body fat, 70.12% of the variability in the model is explained by age. Typically, if this is, 80% above, that's a very good predictor. But, here age is a good predictor also. 70%, almost 70% of the variability in body fat and the model is explained by age. So age is a good predictor. It's not the only one that explains body fat because here we have 70%, right? So means that if we were to want to build a robust model, we can add other type of variable that explain body fat. All right. So one last concept, and I will be taking questions. That last concept won't take long. The last concept has to do with obtaining random sample, a sample random sample. So I was at a computer fair, and at the end of the fair, they had a demo, and at the end they put the names on people on a hat to draw prizes. So the people who were selected from that type of drawing will win some software. And the thing about that kept my attention. That caught my attention is that they were using Excel during the demo. They were using Microsoft Office and during the demo. So, and then I was wondering how come they couldn't just use randomize using Excel as opposed to putting the names on the head. You see, when you put names on the head to shuffle and then select, the idea is that you want to achieve randomness. The problem is, okay, how big is the head or how big is the container? And even when the person comes to select the winners, quite often people tend to select what they see on top, or, you know, even when you try to shuffle to make sure it's well randomized, you don't achieve that. So with that in mind, I'll show you. So let's suppose that we have a presentation, you know, so a lecture, and then at the end we want to give prices. Every attending member has a number. So for simplicity, I just numbered the people 1, 2, 3, all the way to the number of people. So in my demo, I have like 52 people attending. So each one has a number. So James has number 1, Jose number 2, and so forth. Now, how do I select winners? Let's say I have 5 prizes to give. How would I select? Okay, instead of using the selection from the head, I can use Excel, the random function in Excel. So here, let me come here, equal rand. It doesn't take argument. So rand. Once I put it like that, let me hide this or delete this. So I put here rand. So function in Excel, it doesn't take argument. Equal rand, no argument. Now you see rand changes as I'm clicking and selecting things. Why? Because it uses the computer clock. But it doesn't matter. Once I select it like that, I just double click so that every observation has a random number. You see, every observation has a random number. If I come somewhere here and click, or I reload or save the document, anything that I do, it will tend to the random number will change. So let's make a change here. For example, I come here, save here. All right, because that random numbers tend to change, what we want to do is copy, we copy it and paste and do a paste special. So let's copy it and do a paste special. We copy and paste special here. What I'm trying to do is fix it so that it won't change anymore. See, as soon as I did paste special, you see the original random numbers change, but that's fine. So this will be the fixed random numbers. When I fix the random numbers, anytime I load the spreadsheet, it changes. So I don't care about this anymore because I already fixed them. So I already fixed them. Then all I have to do is sort, select the data, and sort by the fixed random number. You have to sort by the fixed random number, not the identifier. Smallest to largest, all right? So if I was to give prices to, let's say, 5 people attending, I just select here. So these are people selected in random fashion. So here I selected 6. So let's not include this guy. So as you can see from the random selection, attendee number 16-1, attendee number 23-1, attendee number 51, attendee 15-1, attendee number 39-1. And all this was done in a random fashion. So with that, I thank you and stop here. And obviously there is a lot to cover. And this is an introductory demo, and I didn't have an idea about what the audience will want to hear or see. So I just selected, you know, a topic very basic. Obviously, with time, we can do other things that pertain to advanced topics and